Today we have bagging, boosting, random forest. I will show you.
Professor, just sorry, one request. May you please answer one of my emails that I
Yeah,
sent?
of course, of
Yeah,
course.
thank you. I sent you some questions.
Yeah, I saw a long list of questions, so I need 1 week to answer to those questions. So
Okay,
wait,
thank you.
so wait
Okay,
after
sure.
a week.
Thank you.
Yeah, detailed mail.
Okay, sure. The sooner the better. Thank you.
Okay.
Mr. Bohosian, how can we have our um, tickets tomorrow? You will send us separately?
You are opening Moodle, finding your ticket for all of you. But in the ticket, you will find why it is personal for each of you. You are just downloading it and starting to work with it.
Okay, thank you.
Was
Okay, we have our slides. So standard problem, not always Zoom can realize that I am a host. Okay, you see slides. We have slideshow, play from beginning. Okay, we have the idea of bagging. So bagging is actually the same as Bootstrap aggregation, just an acronym coming from this short description actually, because you understand that if you have Bootstrap aggregation, then you are performing bootstrapping. It means that you are multiplying your training sets. If you have one, now you have maybe 1,000 or 100. For each training set, you are growing your individual decision tree, no matter is it for classification or for regression. Both methods are working exactly by according to the same idea. Here we have bagging. Yeah. So we have, you see here, we have one parameter, big B. So we are performing bootstrapping and getting big B different training sets. Then for each training set, we are growing individual tree. Aggregation means that finally we are trying to accumulate the results that we have from different decision trees. If this is regression, we are calculating the average as a prediction. Like this, we have here the formula. So each tree is giving us a number. If this is regression problem as a prediction, we are just accumulating all those numeric values and calculating the corresponding average. So you have big P different decision trees. So you have big B different numeric values. That is why average is average of this big B different numeric values. And the final number we are showing as a prediction. In case of classification, we don't have numbers, we have classes. And in this case, we have two approaches. One approach is to take a majority vote. So you have as a prediction as a class. So decision trees are predicting some of the classes. So you are just calculating within your prediction set how many times you saw prediction of class 0, prediction of class 1, prediction of class 2, calculating the percentages. Then the biggest one, the biggest percentage, you are taking as a final prediction of a class. Or maybe you can take the corresponding probabilities, because different machine learning approaches, before returning a label, actually they know the corresponding probability, and they know that when this is bigger than 0.5, then it's from one class. It's smaller than 0.5, it is from the other class. When you have multi-class classification problem, for each class you have the corresponding probability, and usually you are taking the probability with the biggest the class corresponding to the biggest probability. So in this case, as a prediction, you can have from each tree the corresponding probability. Then you can accumulate those probabilities because they are numerical, they are numbers, they are numerical variables. So you can calculate the corresponding average of the probabilities, and then based on this probability, decide the class of the corresponding observation. We compared here once both methods showed that for this particular example, they are behaving similarly, but expect that in practice, you will see also different results. And we saw disadvantage of bugging, one of the disadvantages, because soon we will speak about general disadvantage of bugging. We can understand that, first of all, bugging is rather complex because you are, instead of one decision tree, you are constructing many different decision trees, and overall it's becoming very complicated in order to finally aggregate the corresponding final result. So this is technical disadvantage, but we are okay with technical disadvantages because now we have very powerful computers. When you need something to calculate, you will find enough resources. One of the biggest disadvantages is actually interpretability, because we mentioned that in case of decision trees, the best thing that we see, this visualization of the trees, which is very helpful because it's just showing the overall interconnections between the variables in our data set. When you are performing bagging, you are losing this power of interpretation. You are increasing the power of prediction, but we are losing in interpretation. You don't have tree. You cannot show tree in case of bagging. There is no any tree. You cannot just draw and show 1,000 different trees and say that, you know what, I'm calculating the average of those 1,000 different trees. It's impossible to perform. That is why we are losing in interpretation. We are gaining some predictive power. Meanwhile, we are gaining some complexity. In case of bagging, we have different parameters. One set of parameters is coming exactly from the trees. When you are growing a specific tree, you have a lot of different parameters to tune. Now, together with this set of parameters, you have also one additional parameter, this big P. So when you are performing bagging, you are going to tune all the entire set of parameters, because for an individual tree, parameters can be different, but as a result of aggregation, the values of parameters can be totally different. So you need to apply cross-validation in order to set the values for the entire set of parameters. It's very complex. And also one very big disadvantage of bagging. So we are now jumping to random forest, but we are trying to understand why bagging is usually not the best way of working with decision trees. The idea is you saw that always decision tree is starting from the strongest variable. When you have the strongest variable, then the splitting of the decision tree, you are starting always with this strongest predictor. Say if you have this football data, and in football data the years is the most important parameter, then for different training sets based on some bootstrapping procedure, presumably you will always start to split your decision trees with this years variable. And this is very problem in case of bagging, because even when you have 1000 different trees, all 1000 different trees are starting with the same parameter years. So your trees are somehow similar to each other, because exactly in the case when you have rather small values of for features, you have 2-3 features. Any question? Okay, so if you have only 2-3 features, the number of features is very small, and one of the parameters is very, very strong, then your 1000 different trees can be very much similar to each other. And it is very bad, because if you remember when we are trying to explain here why bagging is helpful, you see, when you have small and independent observations, you see the most important thing in this theorem, when you have Z1 and Zn different variables, random variables coming from the same distribution, but the most important thing that they should be independent. So when they are independent, this is how theorem is working. So when variables are independent, in your case, you can understand independence as a correlation coefficient. So correlation coefficient should be close to 0. And when each is coming with the variance sigma squared, the variance of the mean, when you are just aggregating the result across different distributions, should be sigma squared over n. So by this n factor, we are decreasing the corresponding variance. But in this theorem, the most important thing is that variable must be actually, not only should be, must be independent. Otherwise, this theorem is not true. Now, the same idea we are trying to apply for decision trees. So we are assuming 1000 different decision trees. And when you are aggregating, calculating the average, assuming that this will decrease the corresponding variance, we need to understand, we need to recall that independence of these decision trees is very important requirement. But the problem is when you have rather strong variable and all your trees are starting with the first strongest parameter, then the second is the less stronger parameter. All your trees are actually the same. They are actually correlated. And when you are aggregating to get the final result by means of averaging, you are not decreasing the variance. You are actually getting the same result as without aggregation. So bagging is not working in this case. Why it is not working? Because your trees are dependent. They are similar to each other. This is the biggest disadvantage of bagging. That is why we are trying to slightly modify this bagging procedure and inventing a new approach known as random forest. So summary that you see here, that this means that bagging will not lead to a substantial reduction in variance over a single tree in this setting. Why? Because this theorem is not working. Because our random variables in terms of different trees are not independent. That is why we are somehow applying a procedure which is leading to random forests that decorrelate the trees. So we need a procedure that will lead to decision trees which are independent, which are uncorrelated. We need to invent something. And the idea you see here when building these decision trees, now we are slightly trying to modify this bagging approach. So we have different training sets. For each training set, we are applying decision trees. Now we need to modify this procedure. So each time a split in a tree, so you can recall that each time when you are trying to decide how to grow the tree, you are taking one by one all features, the first one, the second one, the third one, until the end one, and you are just checking which one is the strongest feature, and if this is the strongest feature, from where I need to cut it. So now the modification is that when you are trying to understand which is the next variable that you are going to split in a tree, you are doing a random selection of M predictors. So instead of considering the entire set of your features, you are just randomly selecting M different predictors, and you are performing the split based on this only M predictors. So you have P predictors. P can be 1,000 different features. Instead of these 1,000 different features, you are randomly selecting small m, and m we are assuming should be rather small than compared to this p. So each time when you are performing split, you are just searching within this small number of features predictors instead of the entire set of p. So if you have the strongest parameter, not always this strongest feature variable is within this set of random selected m predictors. And this is good because we don't need each time to start the tree with the strongest parameter. So when you are performing random selection, usually the strongest parameter is playing outside of your random selection. That is why he's not participating in the split. And when you are looking to your different trees, you see that some of them are starting with the strongest variable. Some of them are starting from the other variables. And there is some randomization between your trees. So your trees are becoming independent, and the theorem is starting to work because when you have different independent variable and you are aggregating, you are actually decreasing the entire variance within your average random variable. So this is how random forest is working. By the way, you need to understand when m, small m, equals to p, random forest is exactly the same as bagging. So in case of one of the parameters, random forest is becoming actually the bagging. So you can try when you are applying random forest and you are just changing this small m as a parameter to tune. One of the cases can be m equals to p. So you are just checking bagging because maybe your decision trees are independent because you don't have the strongest variable. All variables are somehow similar. And when you are changing the training sets, you need to remember that decision trees are very sensitive to your training set. When you are performing bootstrapping, changing the portion of your training sets, so training sets are becoming slightly different. Decision tree, when you are applying, is giving sometimes totally different result. That is why sometimes bagging can work, sometimes bagging is not working. It is depending on your specific data set on your specific application. But in any case, so you have parameter m, you're just trying to tune this parameter m. One of the possibilities is to take m equals p, this is bagging. So you are checking bagging, then checking random forest with different m's and taking the best approach. But there is a general recommendation. So each time when you are trying to select m different predictors, one of the best choices should be m equals squared p. So square root p. So when you have 100 different features, the best choice maybe is should be around 10. Each time, instead of taking 100 different features, you can take 10 randomly selected features, and based on these 10 different features, try to perform your tree growing process. This is how it works. So you need to understand that random forest is a modification of bagging because we are trying to decorrelate our decision trees. And this decorrelation is usually connected with randomization. So we are taking some random set of M predictors and performing this tree growing process exactly for these M predictors. Very, very general procedure. And this is actually how random forest
Wait,
and actually the bagging is working. You have,
may, I'm
let's,
sorry.
okay, let's finish this
Okay.
visualization, then you will ask a question. So this is the same as we already described. So you see, we have tree 1, tree 2, tree n. No matter this is based on random forest or based on bagging, because bagging is also within the random forest. And the idea you see, tree 1 is saying that your observation instance is from class A. The second one is saying from class B. The third one can say it from class C, class B. Just calculating the percentage, how many times you saw B, how many times you saw A, C, just calculating the number of the corresponding predictions. And the biggest prediction you are sending as a final prediction. Yeah, if you have any questions, go ahead.
Yes, I was trying to ask when increasing the number m, are we risking overfitting or just risking that all the trees would look the same?
The problem here is not overfitting because overfitting is a general ML problem. So at this moment, forget about overfitting. The problem is then you are applying more complicated approach. Bagging is rather complicated compared to a single tree approach, but finally you are getting the same result. This is the problem, that we invented a new approach, bagging. We are doing bootstrap aggregation, but the example that finally you are doing some comparisons finally, bagging compared to a single decision tree. Finally, you see that there is no any improvement. This is the problem. Why? Because all your decision trees within this bagging are correlated. So when you are calculating the average, you are getting random variable with the same variance. So there is no improvement. This is the main problem. That is why if within your data set you have a problem as a strongest feature, as a strongest predictor, and you are increasing M, finally the result is becoming the same, exactly the same as for a single decision tree. That is why you need to be careful when you are just tuning this parameter. Always start with smaller values of M. Compare the small values of M squared P. Square root of P is the best choice. Around this, first of all, perform some tuning, some optimizations. Then you will see is bagging working or no, compared with a single decision tree. And you see here, so we have different examples with different values for M. We have M equals P. This is this orange curve, which is actually our bagging. This is bagging. Then the second one, this blue one, light blue one, M equals P over 2. So we are each time we are randomly selecting only the half of the variables that we have and performing random forest based on it. You see that in this particular example, of course, because for your specific examples, you can find totally different picture. You see that blue and yellow or brown, as you see on your monitors, the corresponding colors actually are the same. But when you are taking M equals square root P, this is the green line. Green line is slightly better, not this dramatically better, but in any case, if you think about 5-10% improvement, then in this particular example, n equals square root of p is the best choice. And we know the theory. Why? Because we already understand that there is a background connected with the central limit theorem, by the way. So I forgot to say that the theorem that always I am showing is the central limit theorem. And in this central limit theorem, the most important condition requirement is that all random variables are independent. Otherwise, there is no way to decrease the corresponding variance of an after aggregation. Any other questions, CM? Okay. Variable importance measure. So bagging typically improves the accuracy over prediction using a single tree, but it is now hard to interpret the model. Yeah, bagging and random forest. In case of bagging and random forest, we have the same problem. So we need to understand that in case of random forest also, we have 1,000 different decision trees. Then we are again finally aggregating. So the difference between bagging and random forest is that the trees, individual trees are different, but the overall aggregation, as in case of bagging, the same as for random forest, is the same. You have 1,000 different trees, and based on these 1,000 different trees, you have an averaging process for regression or majority vote for for classification. And you have problem with interpretation. So you don't have trees. You cannot understand which variable is the strongest. So we have hundreds, thousands of different trees, and it is no longer clear which variables are most important to the procedure. That is why in case of Python and in case of R, when you are completing the procedure, you have possibility to look into the list of the variable importance because you don't have interpretability. You don't see the strongest variables. That is why we have this functionality. Finally, you can try to understand, do you have the list of important features or all features are comparably the same. So we can have possibility to have these relative influence plots. So there are different approaches when you are trying to calculate which predictor is the best. So here I am trying to describe just one of these approaches, but I am going to show you the final results. This is how this relative importance is working. Why relative? Because the strongest variable you see for this car seats data, this is price. So price is always starting with 100 because we already scaled it. So the strongest variable is starting with 1 or with 100. This is relative importance. And the others we are showing relatively to the strongest variable. You see that this is the result of our software environment or the result of Python, no any difference. Importance is giving you some numbers from 0 to 1 or from 0 to 100. When you are plotting, you are actually seeing the difference between different variables. So price is the most important variable. Then we have shell below good, bad, because we had a categorical variable. So we have shell below good. So you see shell below is somewhere 52, 53. So you have the strongest variable here. So in this case, bagging is not working very well, we can assume, because you have price as the strongest variable. And the remaining variables are decreasing in their importance until USES is the most unimportant variable. So you understand you can cut from somewhere. You can cut, for example, this USES, education, travel log, medium, population, maybe income, and start from somewhere from the age and to price, assuming that these are your important parameters. And in all cases, when you are working with random forest, with bagging, with boosting, with other ML approaches where you have problem with interpretations, you are not able to understand which variable is the most important. As an output in all these functions, we have the corresponding relative importance or importance functionality. And based on this functionality, we are getting the final list of importance. And by the way, what kind of description I have? I see a question here. Let's see. Can you please explain how this information is obtained? Yes, I can explain it. So you see here the description of this approach. So for bagging and random forest, for example, regression trees, you understand that the same we are here. We have for classification trees. The problem is that for regression and classification, we are using different measures. So in case of regression, we record the total amount that the RSS is decreased due to splits over a given predictor. Recall that when you are constructing decision trees, each time you are picking one of the variables, splitting by this variable, and going and looking to the corresponding RSS. Each time when you are doing the corresponding split, you know how much you decreased the RSS for the corresponding features. Says the first feature, X1, you tried several times when you are growing the tree. Several times means 100 different times you tried this, then throw away, then again return to the same split. 100 different times you know that this specific parameter decreased the corresponding RSS by some amount. Just gathering all those decreases, calculating the average, and then finally comparing all these averages. And you understand that when you see in your decision tree the strongest parameter, not always the strongest parameter is the same as you will see in your list of important features, because one of the procedures that I'm describing here is based on an averaging procedure. Even when you are not splitting by the corresponding feature, you are somehow checking how much he decreased the corresponding RSS, storing the corresponding number. Then at the end, you have the corresponding stored variables. You are just picking and calculating the average. That with different features. Each time I'm checking which one is giving me the best decrease in RSS. But in any case, if I am not using it, I am just trying to store the corresponding value and trying to understand finally the average decrease of RSS based on the corresponding feature. And these average numbers I am showing finally as a relative importance in average. And that is why I am saying that when you have an individual tree and you see that, for example, this individual tree is starting with variable, for example, price, not always the strongest parameter you will see in the corresponding list. Why? Because the procedures are somehow different. In case of relative importance, you are calculating the average importance. Why just decision tree is saying that, you know what, when you started the decision tree, that single time at that point, the best feature was the price, only once maybe. But in average, the other parameters can impact the RSS better. And similarly, when we are jumping to classification trees, remember that in this case, instead of RSS, we are using information. We are using, for example, information gain, or we can use the corresponding error rate of the classification. There can be different possibilities. So each time when you are splitting, you are trying to understand the decrease in the Gini index or the decrease in the error rate. You are just storing the corresponding numbers. And when you just completed the procedure, you are remembering the stored values, calculating the corresponding averages, and returning the list as a relative importance for your features. And by the way, this is not only the only procedure that we know. There are a lot of different other procedures that can finally somehow summarize the importance list. This is just one of the simplest scenarios that we can perform. There are many other different approaches for variable importance. And the problem is that, as usually in case of machine learning, when we are trying to compare different algorithms, the list of important parameters can be different because it depends underlying logic that you are applying. You see that we have two approaches for importance, just individual decision tree and aggregation of the final results. They can be totally different. And we know why, because decision tree is showing the importance for, for a split in that specific timestamp, while the relative importance is showing the average importance. The logic is different. That is why we are expecting that the final result can be different. Okay, and we have this relative importance. Then we have boosting. So even if we saw that USES is not important, there is a chance it would be picked in random M variables, not be picked in the random M variables. Random M variables which we are picking are not connected with the importance. We are picking them randomly. Each time we are picking random M parameters, we don't know are they important or not important. We don't know it. If you have 100 different parameters, different features, variables, and small m equals to 10, each time I am randomly selecting 10 different features. I don't know, maybe at that timestamp, all 10 different features are will come with the smallest relative importance, no matter I'm using them. So one of my trees will include only the strongest features. One of my trees will include the, the variables with the smallest importance. The other can maybe include the mix of those variables. I don't know. The idea that when you are seeing US yes in your list of importance at the end of the list, but when you have a individual tree, not bagging or boosting, just an individual tree, one of these individual trees, even when you are using all the features, by the way, can start with this USES, because maybe at that starting point, decision tree found that the most important variable is this US yes. Maybe it is possible. I saw this many times when I try to apply decision trees for this relative importance. When we are comparing, the results can be totally different. The most important variable in your relative list, you you can never see in the decision tree because it's showing an average picture, while decision tree splitting is saying, remember that this is greedy approach. It is saying that at this moment when I'm trying to understand from where to start, I'm starting with the parameter which maybe in average is not the most important. And don't be confused when you are seeing that the results are different. In machine learning, results are usually different. That is why always when I am giving you some problem, the most important thing is not just to get the final result. You saw it in the midterm. I don't going to just understand how you are writing the codes. I am trying to understand how you are interpreting the results, how you are comparing the results. This comparison and understanding is the most important part in machine learning. Now about boosting. So the idea is boosting is totally different. Boosting, yeah. Okay, the idea of boosting is totally different. This is not the same as bagging. So how we can understand boosting is working? Recall just your calculus lectures. I am assuming that you know what is Taylor series. When you have expansion of a function into a Taylor series for different elementary functions, when you are adding more and more terms, you are getting more better approximations of your functions. Boosting is working like this. So we have decision trees we are taking one decision tree as an approximation of our prediction. Then we are saying, let's add the second tree, tree 1 plus the second tree. Maybe prediction is not very good. Adding the third tree, plusing always. So we are trying to approximate our predictions by a series of traces, uh, trees, by a series of trees. So boosting, like bagging, boosting is a general approach. Yeah. By the way, very important thing. All those things, boosting, bagging, and random forest, are known as ensemble methods. Why ensemble? Because we have aggregation of final results. We don't have one individual tree. When you are using different trees and then in average you are getting prediction, this is known as ensemble method. So boosting is a general approach that can be applied to many statistical learning methods. Yeah, by the way, not only for decision trees, but for other approaches, we can apply boosting, and both for regression and classification. So the trees are grown sequentially, like in series expansions. Each tree is grown using information from previously grown trees. So we are growing a tree, using this tree for predicting something, then the result we are using for growing the next tree. So these trees are depending to each other. The second tree is based on the result that the first tree is giving. The third tree is using the result that the first two trees were giving, are giving. So each next tree is using the information from already existing trees. In bagging, this is not the same. In bagging, we have totally independent trees, and we need them to be independent. Otherwise, aggregation will not decrease the final variance. And by the way, one very important observation in case of bagging. If you remember, we bagging and random forest. If you remember, we have pruning technology. When you are using individual tree as a prediction approach, we are always pruning the tree. We are just cutting some of the leaves because we need small trees in order to overcome this overfitting. Remember that in case of bagging and random forest, we are not pruning the trees. We are growing a very big trees because we know that after aggregation, this will help us more, because in this case, the trees can be decorrelated, while after pruning, they will become more correlated. That is why we are not pruning the trees. We are growing 1,000 different big trees, trying to overfit each time by the individual tree, because we know that after aggregation, we will somehow overcome this overfitting. In case of boosting, the situation is totally different. We are growing very small trees, just using one or two splits, and then jumping to the next tree. We are always growing very small trees in order to overcome the overfitting, because each individual tree in this case is very important. The first tree trying to predict, then the second tree is using the result of the previous one. The third one is using the result of the previous two ones. That is why in this case we are using only small trees. Just sometimes you will see split equals one. You have only one split, which means that you are in case of segmentation, you are just splitting your entire feature space into two domains, using this as a prediction. Then the second tree is coming with again one split. Then the third tree is coming with one split. But even with this one split, when you have 1,000 different trees applied sequentially, this boosting is very powerful. And now it's very comparable to support vector machines, and in many cases comparable to the results that neural networks are giving you, because boosting is now very popular, it's very trendy, and it's very powerful. So now the idea, given the current model, so we have some training set, we fit a decision tree to the residuals from given the current model. Current model means we have decision tree. So we are applying decision tree to our training set. subtracting. If you have a regression, let's assume that we are working with regression. The classification can be explained exactly by the same way. Assume you have a regression. You have an output. This output are numeric values. This is a numeric variable. You are trying to predict it. So you are applying individual decision tree, predicting these outputs. You have some approximation, subtracting your output from this approximate prediction, getting the residuals from the model. Now the second decision tree, you are applying to the residuals, not to the training set, but to the residuals. You are getting a model, subtracting from your residuals the corresponding prediction, getting the second order residuals, much smaller ones. The next three, you are applying to the residuals, subtracting, getting new residuals, subtracting, training. So each time when you are training a specific model, you are training this specific model to your residuals. Each time you are trying to reduce the prediction error that you are getting for your residuals. So each time applied to the residuals, you are trying to predict them better and better. And after 1,000 iterations, you are actually getting the final prediction of your training data. So we have some parameters here. Each of the trees can be rather small with just a few terminal nodes. So we have D parameter here, the number of splits. Of course, you need to tune it. So based on some cross-validation procedure, you need to understand how many splits you need to use, 1, 2, or 3. Usually 1, 2 is enough. You need just to understand, apply 1 split or 2 splits. By fitting small trees to the residuals, we slowly improve prediction. This is the most important part, that boosting is slowly improve predictions. Otherwise, we will overfit it. And in order to slowly improve, we need to have a small number of splits. And we have also the shrinkage parameter lambda, which is learning rate. Usually you need to also tune this learning rate. You see here the description of the algorithm. The final prediction, this last fx, is sum of different decision trees, and you see here this learning parameter. It is somehow describing how slowly we are improving the results. It's very difficult to understand which values to use, because for different applications, this lambda is different. Sometimes you need to learn slow. Sometimes you need to learn faster. One of the approaches that you will encounter in Python is AdaBoost. AdaBoost, Ada is standing for adaptive learning rate. So in this case, you are starting maybe with bigger learning rates. It depends on your data. Then you are just changing the behavior of your lambda into increasing or decreasing it, taking it somehow adaptively. That is why one of the boosting approaches is known as adaptive boosting. It's very powerful approach, because in this case you are struggling this overfitting by changing the value of your learning rate. Maybe some at the beginning you need big lambdas in order to learn faster. Then when you are learning faster, your residuals are becoming smaller and smaller. You need to somehow decrease the rate, because otherwise you will overfit your residuals. That is why maybe you are starting with, roughly saying, some big trees because they are learning faster. Then this learning rate is uh, somehow helping you to improve slowly and slowly. This is how boosting is usually working. And here is comparison. You see that boosting with depth equals 1. Depth is the number of splits that you are using in your tree. You see that when depth is 1, you have only 1 split. When depth is 2, you have 2 splits. And here comparison with random forest with m equals square root of p. You see, at least for this particular example, the worst result we have for random forest, not always this be this should be the truth, because random forest also is approach that can be outperform in many cases boosting. It depends on your data, it depends on the optimized values of parameters that you are using. Then you see that blue one is depth 2. It's interesting that depth 2 means that your trees are more powerful. When you are looking into your individual tree with 1 split or with 2 splits, Two split is more powerful because it is using more segmentation of your feature space. But as a result of boosting, the simplest one with one split is actually the best. This is very interesting how boosting is working. So as much slowly you are learning, as better final result you are getting. So you need to learn slowly. Slowly learning is helping not to overfit the data. So this is comparison of random forest or boosting with one split and boosting with two split. So you have a choice, use one split or two splits, no more. Otherwise you are actually coming close to random forest. Yes, you have a question?
Yes, in the previous slide, we had R. What's the
Which one?
yes
These
yes
are
here yes we have
residuals. These are residuals.
residuals and why we
Yeah,
set
you
f
see
hat
here ry
f
equals our output. This is at the first step. We have output. We are applying decision tree to this output. Then we are subtracting. You see, RE is residuals minus what we applied already. And iteratively, our output is becoming the residuals, and we are trying to predict the residuals. So -3 to residuals, -3 by some learning rate. And then finally, when you are trying to understand what kind of prediction you have prediction as a lambda multiplied by the first three, plus lambda multiplied by the second three, lambda multiplied by the third three. And if the learning rate is a constant, you are multiplying always with the same lambda. If lambda is selected as adaptively, so each decision tree is multiplying by a different lambda.
and because we work with the residual we set f hat equals to 0 because we want
Sorry,
to why we set f hat equals to 0
which
set
one
f
equals to 0?
set f hat x equals to 0.
This is the first initialization stage, initializing our approach. The first tree is 0. Then we have the first tree, then the second tree, because we need to use it in a sum. So this iteration needs some initialization, initial setting of our parameters. So there is no any decision tree, because here we are summing f equals f plus lambda multiplied by the first tree. The first tree should be 0. That is why this is initial point. Initially, we have output equals to residuals, although these are not residuals. These are exactly our output. But in order to use this iteration, summing and subtracting, we need initial values. And then you have some iterations, something like a four cycle.
Thank you.
Yeah, we have a question about previous topics. Let's conclude what we have, then we'll return to entire questions. So here we have final stage, understand the values of parameters. So which parameters we are going to tune. So in case of boosting, we have the number of trees. This is one of the important parameters. Unlike bagging and random forest, boosting can overfit if B is too large. So we need to tune it. In case of aggregation bootstrapping, as bigger is your B, as better results you are getting, although you have a saturation. So bigger values means bigger complexity, but the results can be the same as for smaller B. In case of boosting, you need to put some limitations on B. You need just to tune it. So we use cross-validation to select B. Then we have shrinkage parameter or learning rate, lambda, a small positive number usually. So we need to tune it. In case of adaptive boosting, we are not going to tune it because adaptive boosting internally adapting the corresponding lambda parameter. So typical values are 0.01 or 0.001. So this is very small positive parameter. Why small? Because we are trying to learn slowly. These improvements should be very slow. Otherwise, we will overfit our data. So very small can require using a very large value of B. We understand that we need to learn slowly, but when you are learning slowly, maybe the parameter B is becoming very big. So there should be a balance between B and between learning learning rate. Then we have the number of splits. How many splits we are going to use in decision trees? One split or two splits. Often you see D equals 1 works well, in which case each tree consists of a single split. So in any case, this is parameter that we need to somehow tune. Now your questions. If you have any questions, let's go with questions. Sorry, I cannot hear you. Can you hear me?
Yes, we can hear you.
Okay. So can I ask a question about previous topics? Yeah, question is about KNN. Okay. We used training data to find the optimal K. Okay, it is true. Training set for KNN is always for K optimization. Given that KNN is a lazy learning algorithm, you can name this it as you want. Why are we fitting the model on trained data into predictions on tests? Not this is the general procedure in machine learning. So we are dividing our data into two portions. One is test data, the other is training data. On training data, we are tuning our parameters. Then when we are trying to understand the objective reality, we are applying already tuned model on the test data. So what do you mean why we are doing in that way? This is the general procedure. You need to understand the optimal K. Applying cross-validation on a training set, you are finding the optimal K, but you don't know are you overfitting the data or no? Because even in case of cross-validation, maybe your prediction and the real test errors are different. That is why when you have a final model, you are trying to understand the corresponding result on a test data. You are just comparing your prediction based on cross-validation and the exact test data. If it's okay, it's working, then you are collecting together your training set and test set and training the final model with the optimal value of parameter that you have. What does it mean? In our notebooks, it was done that way. We are always doing it in that
Uh,
way. You're
I'm
always splitting your data into training and always splitting into test. This is the best way to do it. Sometimes, of course, when we are showing just the corresponding functions and the corresponding codes, maybe it is possible to exactly apply the cross-validation on the entire training set. It's also possible, but the correct way to work with different applications, you have some data set, always dividing it into training set and test set, tuning your parameters on a training set, checking are you overfitting the data or no. You need this final check. Applying already trained model to your test data. If the results are comparable, you know that you already tuned your parameter in a best way, in the best way. Collecting again training set, mixing with the test data for getting the final model because you need to use all available observations. Then the final model you are using for your applications. This is the way how usually we are doing it. And for midterm, you will have exactly the same problem. We are giving you a data set saying using this train test split your data into training and test, apply KNN, logistic regression, and QDA, or other things on a training set, and the corresponding result check for the test data to see and understand the comparison. Are you overfitting or are you underfitting? How your models are dealing with training data and test data.
I understand why we are splitting the data and we use training data to find the optimal K. But after finding the optimal K, we in some notebooks we use that optimal K to fit the model on the whole data set, both training and test data. But shouldn't we be using only test data for fitting the optimal model?
Yeah, you need to use test data. You need to use test data.
Yeah, in our okay, this makes sense because we use the whole data, and I was asking why shouldn't we use
So
the
you can do the both things. Actually, the right way to understand how your model is behaving is to apply it only to the test data, because on the training set, you already know the corresponding results. Of course, you can check in some cases also for the entire data set, but the best way is to train your model on the training set, then to check it on a test data. Why? Because you are trying to check it for unseen observations. You need to check it for new observations that your model didn't see before. This is the way how we are dealing with test data. When you see that the results are acceptable, that on the training set and on the test set you have acceptable results, for a final training, you are just collecting together your training set and test set, collecting together and training the final model with the optimal parameter that you already found. And then the final model that you have trained on the entire data set, you can apply to the entire data set just to check the final result. Even you can apply cross-validation somehow to predict the test error or maybe test accuracy.
Okay, thank
So
you.
in case of midterm, you are exactly need to apply the corresponding model to the training set, then check exactly on the test data without mixing these training and test data. So correct your notebooks if you see something strange there. You can correct everything you want.
So,
Uh,
Mr. Promotion, excuse me. So we should fit X, Y test and test Y test and X test in the fitting. After getting the optimal K and getting the model, we should fit it for the test Y test and X test. Yes?
No,
No?
it depends on what your problem is saying. When your problem is saying train your model on the training set, you are training only on the train set. When it is saying just apply to the test data, it means calculate the corresponding regression or accuracy measures, specificity, recall, precision, everything. Apply on the test set means that you already have trained model. You are only applying to get the corresponding measures. You are not training your model on the test data. You are
Thank
only
you.
applying your already trained model in order to get the corresponding measure, if the problem is saying in that way.
Okay.
Otherwise, there is no reason to split into 80 and 20 percentages and train your model separately for the training set and test set. It's useless because in case of test data, you have very small number of observations. Your model, of course, will work worse on the test data than on the training set. So you are applying only on the training set, getting the model. If you need, you are optimizing some of the parameters. You are understanding which parameter is the best, applying on the training set with this optimized best parameter, you already have the model. Then only for calculation of different measures, you are applying this training set to the training data and separately to the test data, then comparing the results to see, are you overfitting the data or no? Nothing else. There is no need to train on the test data. It's useless. Don't do it. You will
oh,
get 0 grade.
Also, will you specifically state which class we consider positive and which one negative, because it is important while interpreting confusion metrics?
I think that in your midterm, there is no differentiation between positive and negative classes, because in all cases, we are asking if one of the classes, say 0 class, is the positive class, draw the corresponding precision recall curve, then assume that the positive class is 1, draw the corresponding precision recall curve, compare those curves, and say me which class we are predicting better. So you are
Okay.
deciding separately that your positive class is 0, then your positive class is 1, and just comparing, then the commenting. You know
Okay.
what, we saw that, for example, the 0 class we are predicting better. Sometimes I am asking why. because you need to go and check, do you have class imbalance problem
Imbalance.
in your data set? Maybe
Okay.
the class that you are predicting worse is the coming with smaller percentage. So you are writing, yeah, I have a class imbalance problem. I have only 10 percentage of this zero class, 90 percentage of one class. That is why my model is predicting this one class better than zero class, because I have class imbalance problem. So some investigations you are
Mhm.
performing. But
Okay.
in midterm, there is no this strict understanding of positive class, because you are doing first for zero class, then the second for the one class. So you have both classes as a positive classes.
Okay, thank you.
In any case, we will have a call at the starting point of your midterm. So you will look into your tickets. Then after 2 hours, we will meet again. You can continue to ask questions. So in any case, we will overcome all technical details. So the ticket should be absolutely clear for you. So read several times, try to understand what we are stating there, how to construct the corresponding models, which one is to compare to which one. It's very important. Read several times, because we have different comparisons. We have training set, we have test set. We need to compare results on the training set and the results for the test data. Then usually we have different classes. We are trying to understand which class we are predicting better, zero class or one class, at least for binary classification problem. But the same question we can ask also for multi-class classification problem. Even when you have 4 different classes, you can select one of the classes as a positive class and try to understand how we are predicting it. Then the second class you can take as a positive class, the third class, the fourth class. So you need to draw 4 different precision recall curves and just compare different classes. Then we have also other comparison. For example, you have logistic regression, you have LDA, and you have QDA. We can ask to compare all of them on a training set, on a test data, and for different classes. So read carefully to understand how you are performing these comparisons. Don't mix all those things together, because otherwise I cannot check the corresponding works. You
Which
always need to exactly understand what you are comparing and exactly comment on that question. Don't just put all possible ROC curves in one place, just on a training set, on a test set for different classes, for different methods. We will just overwhelmed with all those ROC curves. Just read carefully what I am asking and answer to the specific question without any noise. That is why we will meet tomorrow 2 times. First of all, before starting your midterm, to understand is everything is clear with the ticket. Do you have any technical problems? Then you will start to work at 11 o'clock. We have again the next Zoom invitation. We are coming together, discussing what we have, what you understood or not understood, discussing for 10, 15 minutes, then continuing to work.
when you say compare the different models on a training set, you mean like the score that we get at the time of the fitting?
Yeah, you are applying your model on the training set, getting a model, applying this model exactly to your training set, getting some classification report. Maybe you are overfitting, no matter. But when we are saying that training set, both models you are applying to your training set and getting the corresponding comparisons. I think that in the tickets, everything you will read very clearly, because we try to separate when we are asking to compare different models, when we are asking to compare the same model on the training set, on the test set. These are totally different problems. First of all, the first one, then the second one, then the third comparison. So they are totally different. Comments should come totally different.
Also, just clarification, in the case of ROC curve, if we have binary classification problem, the area under the curve is the same, yes, for both classes?
Yeah, in this case, you don't need to draw different classes. You have
Yes.
ROC curve, you have only one accuracy,
Mhm.
and you have only one AUC. You have
Yes.
different two methods. For these methods, you are drawing only two row curves. There are no any positive and negative classes because row curves are, maybe they are different, but their performance is
Area
the
is the
same.
same.
Array is the same, performance is the same. There is no matter how you are working with the positive class or you are
Yes.
working with negative class, because row curve is working with both classes
Mhm.
simultaneously.
Yes.
It's just collecting both classes. That is why you have for two methods only two row curves, only two AUX, and only one comparison, the final result. You are saying for
Yes.
this method, the AUG is the biggest, it's performing the best when you don't mind about positive, negative classes. If you mind, if you try to understand, then you have precision recall curve. In case of precision recall curve, you are drawing it for each class separately because your precision and recall are class specific.
Very different.
Yeah,
Yes.
they are different.
Thank you.
You can get excellent result for one of the classes and very bad results for the next class. It's possible.
Okay.
Exactly also in the cases when you have class imbalance problem. We have such an examples, by the way, in our data sets. One of the multi-class classification problem is coming with class imbalance problem. So be careful when you are trying to answer to the question why this class is performing the worst, because the percentage of observations is the smallest. It's very simple observation, but you need to write it.
Yes. Thank you.
Okay, let's finish today's lecture. Tomorrow at 9:10, let us have a call. Before it, you already will have uploaded from my site the corresponding ticket as a PDF